Researchers often study the characteristics of a distribution of scores. We are interested in characteristics such as shape, center, and variability of the distribution. These are all characteristics of a group of scores, but what about individual scores? Aren't they of interest? Indeed they are. In fact, knowing the characteristics of a group of scores helps us better understand individual scores. One way to study an individual is to look at how he or she fits in with the group. Have you ever done poorly on a test, as I have? If so, one of the first questions you may have asked was, "How did everyone else do?" That's certainly what I wanted to know. I wanted to understand the relative position of my score when considered within the group. If almost everyone did poorly, so that my score was typical, or maybe even above average, for some reason that made me feel better about myself and my performance on the test. Just as we have statistics that describe the characteristic of a distribution, we have statistics to help us understand the relative position of scores. In this video, I'm going to look at 5 such relative position statistics. Let me list them now, then we'll look at them each in turn. The deviation score is the distance from the mean. It is given in the unit of measurement. A z-score is also the distance from the mean, but it is given in standard deviation units. A percentile rank is the percentage of the cumulative frequency below that score in the distribution. A percentile is the score associated with a specified percentile rank. Quartiles are special percentiles that divide the distribution into 4 equal parts. Let's start with deviation scores. A deviation score is a score's distance from the mean. The formula for a deviation score is to subtract the mean from the score. Here's a sample of scores taken from a distribution of scores that has a mean of 20. A score of 25 is 5 above the mean, so the deviation score is 5. A score of 20 is at the mean, so the deviation score is 0. A score of 15 is 5 below the mean, so the deviation score is -5. Notice that 25 and 15 are both 5 points away from the mean, but one is above the mean and one is below the mean. This is indicated by the sign of the deviation score. We can also look at how far away a score is from the mean with z-scores. The difference is that a z-score is not in the original units of measurement, but in standard deviation units. To accomplish this, we divide the deviation score by the standard deviation. Here's an example to help clarify this concept. This is the same sample of 5 scores, again drawn from a larger sample. Let's say that the mean of the larger sample is 20 and the standard deviation of the larger sample is 5. As in the last example, a score of 25 is 5 units above the mean, so it has a deviation score of 5. This deviation score happens to be the same as the standard deviation, so a score of 25 is 1 standard deviation above the mean of 20. The z-score is 1. A score of 20 is right on the mean, so the z-score is 0. A score of 15 is 1 standard deviation below the mean, so the z-score is -1. Why put scores in standard deviation units? The main reason is so that we can compare relative position of scores from 2 different distributions. Z-scores let us compare apples and oranges. Suppose that 2 friends are taking the same subject in school, but they are in two different sections. They compare their final exam scores and find out that one of them received a score of 80 and the other received a score of 70. Now, if they don't know anything about statistics, they'll assume that the score of 80 reflects better performance on the test. But what if the person who got a 70 earned a lower score because the test was more difficult in their section of the course? It's possible that the person who scored 70 was above the mean in their section of the course, and the person who scored 80 was below the mean in their section. Just for the sake of discussion, let's say the person who scored 70 was one standard deviation above the mean, and the person who scored 80 was one standard deviation below the mean. Those z-scores are 1 and -1, so suddenly our perception changes. The person who scored 70 performed better than the person who scored 80, at least when you take into consideration the different tests and how students scored on those tests. Z-scores have many useful purposes in research, and I discuss some of these purposes in other videos. The next two relative position statistics are percentile rank and percentile. A score that has a specified percentage of the scores beneath it is said to have that percentile rank. A score with that percentile rank is said to be at that percentile. This seems terribly confusing, so let me provide an example. Rachel has a score of 60, and that score is above 82% of the scores in the distribution. We say that a score of 60 has a percentile rank of 82. The percentile rank tells us what percentage of scores are beneath Rachel's score. Percentile is sort of the opposite. We would say that 60 is the 82nd percentile. It's easy to get these confused. Percentiles are actual scores in the distribution. We say 60 is the 82nd percentile because 82% of the scores are beneath it, yet 60 is Rachel's score. We can say that 60 has a percentile rank of 82 because 82% of the scores are beneath 60. The terminology takes some practice to get it correct. The most common mistake I hear regarding these terms is that someone will say they had a percentile of 90 when they mean that their percentile rank is 90 because 90% of test takers scored beneath them. Their percentile rank is 90 and their percentile is the actual score they received. Once you understand percentiles, it's an easy leap over to quartiles because they're just special percentiles. The 25th, 50th, and 75th percentiles are known as the first, second, and third quartiles. That is, the first quartile is above 25% of the scores in the distribution. The second quartile is above 50% of the scores. And the third quartile is above 75% of the scores. It may strike you that the 50th percentile, which is the second quartile, has another name. It's the median. The median is the score that separates the bottom half of scores from the top half of scores. One final term. Percentiles and quartiles are subsets of what we call quantiles. A quantile can be anywhere on the distribution. If we break up the distribution into 100 equal parts, we are breaking it into percentiles. A percentile is what we call a 100 quantile. If we break up a distribution into 4 equal parts, we're breaking it into quartiles. A quartile is a 4 quantile. There are many other types of quantiles. For example, we could break up the distribution into 1,000 equal parts. That would be the 1,000 quantile, which also has a special name, but let's not get carried away. If you know the special quantiles that are called percentiles and quartiles, you are in good shape in the world of statistics. When we are studying some entity or individual, we can better understand the characteristics of each unit of analysis if we can view the measurement of a unit in the context of the larger distribution. Relative position statistics are important in studying individuals and individual units.